Welcome to the deep dive. Today, we're tackling, well, one of the biggest questions out there. Does our universe actually have an edge? It's one of those things that, immediately messes with your head. Try picturing a cosmic wall. Where does it end? But then again, an infinite universe, that's just as hard to grasp, isn't it? You start wondering, okay, what's outside? Or what's it all expanding into?
And those are brilliant questions. That's exactly what we're aiming to unpack for you in this deep dive. We'll journey through what cosmology tells us and, importantly, clarify what edge even means in this context because, well, it's not really a simple fence.
Right. So we've got the sources you send over, and our mission is to dig into them, explore these different kinds of edges, apparent edges, physical ones, maybe even edges in time, and see what they tell us about, well, everything. Okay, let's dive in. Where do we start? Maybe with something a bit more familiar, like the idea of a horizon, like being on a boat, you see an edge to the water, but you know the ocean keeps going.
That's a perfect starting point. We absolutely have something like that cosmically. It's the cosmological horizon, our universe's apparent edge. It's basically defined by the oldest light we can see, light that started traveling towards us just after the Big Bang. That light's been traveling for 13.8 billion years.
Okay, 13.8 billion light years away then.
Well, not quite. Because while the light was traveling, space itself was stretching, expanding. So the spot where that light came from is now much, much farther away. About 45 billion light years, actually. That's the co-moving distance.
45 billion. Okay, so that's the limit of what we can see purely because light from further away hasn't reached us yet.
Exactly. It's an information horizon, not a physical barrier.
So it's not like if you could magically travel faster than light, you'd hit a wall there.
Nope, no wall. There's almost certainly more universe beyond that 45 billion light year mark. Loads more, probably. It's just invisible to us forever, unless something fundamental changes about physics.
Right. Okay, that makes sense for the observable edge. But it kind of brings us back to the really big question. Is there a physical edge somewhere out there? A real end to space itself?
Okay, so the short answer, based on everything we know, no. The universe doesn't have a physical edge like a wall or a boundary. But, interestingly, that doesn't automatically mean it has to be infinite.
Wait, how does that work? Finite but no edge.
Yeah, it's a bit counterintuitive. It comes from Einstein's general relativity. The theory allows for space itself to be curved. If space has what we call positive curvature, it could be finite in volume, but still have no boundary.
Okay, need an analogy here. Help me picture that.
Think about the surface of the Earth or a beach ball. That surface is two-dimensional, right? It's clearly finite. You could paint the whole thing. But there's no edge you can fall off. You could just keep going around.
Right, you loop back eventually.
Exactly. A positively curved universe would be like a 3D version of that. Travel far enough in one direction, and you could, in theory, end up back where you started. Finite, but boundless.
Okay, that's one possibility. What are the others?
Well, space could be negatively curved, sort of like a saddle or a Pringle chip shape, extending infinitely.
Right.
Or it could be flat, like a perfectly flat infinite sheet of paper in 3 dimensions.
And which one is it? What does the evidence say?
This is where it gets really interesting. Cosmologists have done incredibly precise measurements, looking at the cosmic microwave background radiation, the leftover heat from the Big Bang. And the data, combined with theories like cosmic inflation, strongly points towards a flat universe.
Flat. Okay, well, that's easier for my brain than curved space, I guess. But wait, if it's flat, does that mean it is infinite?
That is the standard interpretation, yes.
Yeah.
A flat geometry implies an infinitely large universe. It means our entire observable universe, that huge 45 billion light-year bubble.
Yeah.
It's likely just an infinitesimally tiny patch within an unimaginably vast, probably infinite reality.
Wow. Okay, just a grain of sand, like you said earlier. But here's where it gets weird again. If it's infinitely large, how can it be expanding? That question always comes up.
It's a classic confusion. But think about that infinite sheet of graph paper again.
Okay.
Imagine the grid lines in the paper are all stretching, so the distance between any 2 points on the paper is increasing. Even though the paper itself is infinite, you'd still say the grid is expanding, right? The scale factor is changing.
Ah, I see. So every region of infinite space is getting bigger, so the whole infinite thing is expanding, even without an edge to expand past.
Precisely. Infinity times 2 is still infinity. The expansion happens everywhere within space itself.
Okay, that helps. So no physical edge, probably infinite space. But there's another kind of edge we need to talk about, right? An edge in time.
Yes, absolutely.
Yeah.
The Big Bang wasn't infinitely long ago. It happened about 13.8 billion years in the past. And since looking farther away means looking back in time, There's a limit to how far back we can look.
The beginning of time itself, in a way?
Effectively, yes. The start of the hot, dense state we call the Big Bang.
So let's paint a picture. What does the universe look like now, 13.8 billion years after the start?
Right now, we see galaxies gathered into groups, like our own local group with Andromeda. And then those groups are part of larger clusters, like the Virgo cluster. These structures are separated by huge, mostly empty regions called cosmic voids. The galaxies themselves are pretty large and evolved a mix of spiral shapes like ours and big, smooth, elliptical galaxies. And crucially, about 1–2% of their ordinary matter consists of heavier elements, carbon, oxygen, iron, all the stuff made in stars.
Which is needed for things like us and rocky planets.
Exactly. Complex chemistry depends on those heavier elements.
So what happens as we use our telescopes to look further away, meaning further back towards that temporal edge? Does it all look different?
Dramatically different.
Yeah.
As you look back, the universe gets smoother, less clumpy, especially on the biggest scales. The galaxies you see are, on average, smaller, less massive. They haven't had as much time to grow and merge.
So fewer of those big ellipticals.
Far fewer ellipticals, yeah. You see more irregular shapes and more spiral galaxies, and they tend to be bluer.
Bluer meaning younger, hotter stars.
That's right. Higher rates of star formation overall. They're also richer in gas, the raw fuel for stars, but poorer in those heavy elements.
So the building blocks for planets like Earth were rarer back then.
Much rarer. It strongly suggests our modern large galaxies were built up over cosmic time by smaller ones merging together.
It really is like watching cosmic evolution in reverse. But things get even more extreme as we push further back, don't they?
Oh, yes. Let's keep rewinding. Go back to when the universe was about 3 billion years old. That light is reaching us from about 19 billion light years away now due to expansion. That period was the peak of star formation in cosmic history. Stars were being born maybe 20 or 30 times faster than they are today.
Wow. A cosmic baby boom?
You could call it that. And the supermassive black holes at the centers of galaxies were also incredibly active then, shining as bright quasars.
Intense. Okay, keep going back. What about around, say, 1 billion years after the Big Bang?
Now we're looking much further, about 27 billion light years away in current distance. Star formation rates have dropped from that peak, but the biggest change is the chemistry. The amount of heavy elements just plummets, maybe only 0.1% heavy elements at 1 billion years.
So rocky planets, basically impossible then.
Very, very unlikely. Mostly just gas giants would form, and you'd find virtually no elliptical galaxies. Also, the background temperature of the universe, the CMB, was much hotter.
Yeah.
Would have been glowing in the infrared spectrum.
Okay, so the universe was chemically simpler, structurally different. What's next as we go even further back?
Around 700 to 800 billion years after the Big Bang, we hit a kind of fog bank, the first edge of transparency.
Fog. What do you mean?
Before this time, the universe was filled with neutral hydrogen gas, which is really good at absorbing and scattering visible and ultraviolet light. Space wasn't transparent like it is today.
So it was literally opaque.
Largely opaque, yes. It took the ultraviolet light from the very first generations of stars and quasars to ionize that gas, strip the electrons off the protons, and make the universe clear. We call this the epoch of reionization.
And that's why infrared telescopes like James Webb are so crucial for seeing back this far. Infrared light could get through the fog better.
Exactly. Webb is pushing into this era. We think reionization was mostly complete by about 550 million years after the Big Bang. But it wasn't like flipping a switch. It was patchy. Some areas cleared before others. That's why we call it a jagged, porous wall.
So Hubble saw a galaxy at 407 million years, and Webb is seeing them back to maybe 330 million years, pushing right up against that foggy era.
Precisely. We're seeing some of the very galaxies that help clear the fog.
What lies beyond that? Can we see signs of the very first stars?
We're getting into the realm of indirect evidence now. Between about 180 and 260 million years after the Big Bang, we look for signals from the neutral hydrogen itself. Techniques like 21-centimeter astronomy tried to detect the faint radio waves emitted by hydrogen atoms before they were ionized. It gives us clues about where the first structures, the protogalaxies, were forming.
Whispers from the cosmic dawn.
A good way to put it, the actual first stars, POP3 stars we call them, are thought to have ignited somewhere between 50 and 100 million years after the Big Bang. Likely massive, very hot, made only of hydrogen and helium, and probably formed in the rarest, densest, fastest-growing spots in the early universe.
Before that, just darkness and gas.
Darkness, neutral atoms, mostly hydrogen and helium, and the cooling afterglow of the Big Bang itself. Actually, if you go back far enough, even that afterglow was visible light, Around 3 million years after the Big Bang, the universe was hot enough that the background radiation would have glowed red. And then, the most famous edge in time, at about 380,000 years after the Big Bang. That's when the universe cooled enough for stable neutral atoms to form for the first time. Before that, it was too hot. Electrons and protons were just a plasma. When they combined, light could finally travel freely without scattering constantly.
And that's the light we see today as the cosmic microwave background.
That is the CMB, the oldest light in the universe we can directly observe. It comes from that surface of last scattering about 45.4 billion light years away now.
And before that?
Before 380,000 years. You're into the primordial soup of the hot Big Bang, unimaginably hot and dense. First, the universe cooled enough for atomic nuclei to form mostly hydrogen and helium nuclei. Before that, just protons and neutrons. Before that, quark-gluon plasma. And right back at the start, pure energy converting into matter and antimatter. What happened before, or to the very instant of the Big Bang? Well, that's where our current physics breaks down. Theories like cosmic inflation describe the first fraction of a second, and they make predictions confirmed by the CMB, but it's still largely mysterious.
An incredible journey back to the ultimate temporal edge. So let's just recap this for everyone listening. We've got this apparent edge, the cosmological horizon, about 45 billion light years away, just the limit of how far light has traveled to us.
Yeah.
Then we've got the question of a physical edge to space itself, and the evidence points to no, suggesting space is flat and probably infinite.
Correct. No wall, no boundary.
And finally, we have these nested edges in time as we look back, the edge of transparency, the edge where the first stars formed, the edge where the CMB was released, and ultimately, the edge representing the Big Bang itself.
That sums it up perfectly. Lots of different edges, but only one, the temporal one, represents a true beginning that limits our view. Even if space goes on forever, time since the hot Big Bang hasn't. There's only been 13.8 billion years. So there's always a limit to how far back, and thus how far away in that sense, we can possibly see.
It really puts things in perspective. The scale is just immense. So, thinking about all this, what stands out most to you listening right now? Maybe chew on this. What would it be like if the universe wasn't flat? If it did have that positive curvature, finite but boundless, like a giant 3D sphere? Imagine traveling and eventually coming back to your starting point. Or think about those very first stars, giants made of just primordial hydrogen and helium, blazing into existence in total darkness. What an incredible sight that must have been. Keep asking those big questions. Keep diving deep. We'll see you next time on Deep Dive.